Hello and welcome everyone. So in this lecture, what I'm going to do is discuss another example, which is the unit sphere, and it's an example of the Riemannian manifold. In the previous lecture, I have discussed one example, which is a standard example, the Euclidean space, and there I did for the Cartesian coordinates and in the polar coordinates. Now, in case of unit sphere, I will calculate the Riemannian metric in Cartesian coordinate, but I will leave the spherical coordinate one for you as an exercise. The calculations are exactly the same as I did for the Euclidean space. So without further ado, let's get into it. So the unit sphere, as you know, we define the unit sphere, the Sn. So you see, you can already see it's n-dimensional. So we define the unit sphere Sn as the all those points of Rn plus 1 such that what happens, the norm of x is 1. Okay, so this is the unit sphere which is sitting in Rn plus 1. So let's say if you have two-dimensional sphere, I'm taking the two-dimensional sphere sitting in R3. So what is the goal? Now the goal is to determine the metric, which is going to be our Riemannian metric, induced on Sn by the Euclidean metric that we have already seen of Rn plus 1. Okay, so that's the thing. I think there is nothing much difficult here. You can all understand. So what do I need? Well, I need that my coordinate map, the phi, the parametrization. That's I need. How do I define it? How am I going to define it? Well, there is a very simple way, and you must understand all these things because I'm assuming that you have studied the topological manifold and smooth manifold thing. You have proved that Sn is actually a smooth manifold. You have actually proved it. Okay, so let's see what we can do. So Sn is sitting in Rn plus 1. So what we are going to do is find a Riemannian metric for an n-dimensional manifold. Okay, so that means locally Sn is n-dimensional. So locally it is homeomorphic to some open subset of Rn. Okay, that's the thing. So for that, let W contained in Rn be open. Okay, so this is some open subset of Rn, and V contained in Rn plus 1 with, I'm taking some condition and you will see why, xn plus 1, the n plus 1th coordinate. So for example, if you are in R3 and you have x, y and z axis, so I'm taking the z axis to be positive. Okay, so xn plus 1 is greater than 0. So V contained in Rn plus 1 with xn plus 1 greater than 0, we open. Then note that if you take the intersection of V with Sn, okay, so this is open where? This is open in Sn. What is this? This is subspace topology. I hope you have studied it. So since our Sn is sitting in Rn plus 1 and I needed an open subset of Sn, so what I did, I picked up an open subset of Rn plus 1, intersected it with Sn, and I got the open set of Sn. This is what the subspace topology is. Okay, in subspace topology, we actually proved that these are one kind of open sets that you can construct using the open set of the ambient space. Okay, So now you can define phi. How you can define? Well, since Sn is an n-dimensional manifold, what does that mean? This means that you have this map, this homeomorphism. What is the homeomorphism? Homeomorphism is that this goes from W, which is some open subset of Rn, to U. Okay, right? That is what it means to be n-dimensional because it is homeomorphic to some open subset of Rn. So how do I define it? Now note one more thing. Note one more thing that note U here is upper hemisphere. Okay, this is the upper hemisphere, and you see that's what's happening. Why am I doing this? Because you can't map the you can't have an homeomorphism of the entire sphere to some open subset of Rn. And one of the simple fact that I have already told you why this is not possible is that entire sphere is compact, while Rn is not. So how can they be homeomorphic? They can't be homeomorphic to each other as a whole. Okay, so you will have to divide it in parts. Okay, that's what's happening. So how do I define this phi? Well, you pick a point from here, your open subset of Rn. So these will be points x1, x2, up to and so on to xn. And again, I'm warning you, these 1, 2, and n, these are just indices, not the exponent. Please take care of that. Don't get confused. Okay. So now I need to map these n points of Rn to this upper hemisphere. But in this upper hemisphere, you have this xn plus 1 coordinate also. How can I find that xn plus 1 coordinate? Well, you have the answer in the definition of Sn. You have the norm of x is equals to 1. What does that mean? This means x1 squared plus x2 squared plus up to and so on plus xn squared is equals to 1. So from there, you can find the value of xn. So what you do, you just take this n tuple and you map it. You map where? You simply map it. You leave these n tuples to be the same, x1 to xn. And the nth coordinate is simply using that norm condition. We have 1 minus x1 squared minus x2 squared up to and so on minus xn squared. And that's your parameterization. And if you have the parameterization, that's all the thing. That's all the important thing that you need to do when you are trying to calculate the Riemannian metric on any manifold. The first difficult task is to have the parameterization. If you have the parameterization, then after that you just need to do some partial derivatives and some calculation and you can have the Riemannian metric. Okay, so up to here is fine. Now, note that so this is the parameterization for upper hemisphere. This is for So to denote it, this is for upper hemisphere. Let's call it 5 plus. Okay. What would be the parameterization if you want to have the lower hemisphere? For lower hemisphere, what will be 5 minus? I think you can guess it. It's very simple. x1 up to and so on xn. And what will be this n plus 1th coordinate? Here it was positive, so of course you are going in the opposite direction, so this will be minus. That's all. That's the only difference. Okay. So this will be for the lower hemisphere. I have told you the parameterization for both upper hemisphere and lower hemisphere. Okay. So now here I'm giving you first exercise. Think how to take care of the part where xn plus 1 is equals to 0. That is, if you are on the sphere, this is equator. This is basically the overlapping part. So what's going on? Think about it. How is going to be uh, how are you going to be take care of that? Okay, this overlapping part. What's going on here? Because I have not included it, but still is going to be managed. Overall, the Riemannian metric that I am going to get from this parameterization is absolutely correct. It's working. So how is it working? Since I have not included this part, so what's happening? How this point, how this equator is getting involved here? Okay, think about it a little bit. Just a little exercises for you. Okay, so I have the parameterization and I will work with the parameterization of the upper hemisphere. So now I just need to find what I need to find. I need to find these GIs. What are these? G of del phi over del xi, sorry, I, and del phi over del xj. Okay, so that's all. And I have told you that how do you calculate these GIs? By doing the dot product of the basis vectors. Okay, so let's find G11. What will be G11? So G11 will be the dot product of del phi over del x1, comma del phi over, oh, I'm sorry, I need to calculate the partial derivatives first. Only then I will be able to calculate this components. Okay, so let's first calculate del phi over del x1. So this is just partial derivative and I am working with the parameterization of upper hemisphere. That means this one. Okay, so this is 5 plus. So what will be the derivative? So I'm doing with respect to the x1. So with respect to x1, this will be 1 and all the other will be 0. And in this case, what you will get? You will get in the numerator, you will get minus 2x1. But in the denominator, you will also get the 2 because of the square root. So 2 and 2 will be cancelled out. Okay. These are simple calculations. So I'm directly writing them down. Square root of minus x1 square minus up to and so on minus xn square. Okay, so this will be with respect to x1. Similarly, with respect to x2, what you will get? This will be 0, this will be 1, up to and so on, 0. Here you will have minus x2, right? So this is square root 1 minus x1 squared minus up to and so on minus xn square. That's it. So similarly, you can see that del phi plus over del xn, this will be 0, 0 up to and so on 1 minus xn square root 1 minus x1 squared minus up to and so on minus xn square, right? That's what you will get. Now this will give us our components. So what will be components using this? So let's find out the components. So first one is G11. So G11 will be the dot product of del phi over del x1 with itself. That's what will be G11. Okay, let's do the dot product. When you will do the dot product of this with itself, what you will get? You will get this 1 plus 0 plus 0 plus 0 and this product of this with itself. So let me write it down. So this will be 1 plus all the other these terms are 0. So this will give you so simply 0, the sum will be 1. And then I am remaining with this n plus 1th coordinate. So when you will take the product of this with itself, you will get x1 squared in the numerator, and in the denominator you will get 1 minus x1 squared minus up to and so on minus xn squared. Okay, that's your G11. Now let's calculate G12. And as I have told you, this is Riemannian metric. Riemannian metric is symmetric. In terms of tensor also, it is a symmetric tensor. So whatever the value you will get for G12, that will be the value for G21 also. So this will also be G21. Now what this will be? This will be del phi over del x2 dot, sorry, x2 or x1, whatever you write doesn't matter. So x1 del phi plus over del x2. Okay. So if I am going to do the product of this, so you will see 1 is getting multiplied by with 0. So this will be 0. At the second tuple also 0 multiplied by 1. So this is also 0. So in case of all these initial n tuples, you will get 0. Plus this n plus 1th tuple will be multiplied. So this will be 0 plus x1 multiplied with x2, and in the denominator you have that same 1 minus x1 square minus up to and so on minus xn square. So you see, just by looking at these, you can literally generalize. So in general, what will be Gij? You see, when I and j are equal, you are getting 1. When I is not equals to j, you are getting 0. Okay, so this is for I equals to j and this is for I not equals to j. Something must have triggered in your ring, in your mind. Okay, does it ring a bell in your mind? It's the Kronecker delta. So this is delta Ij plus, here in the numerator what you have, in case of I equals to j, this is simply xi squared. Here you have the multiplication. So simply write xi, oh I'm sorry, okay. So simply write xi multiplied with xj, and in the denominator you have 1 minus your x1 squared minus up to and so on xn squared, right? So these are the metric component. So here is another exercise. What I have done up to here, that I use the parametrization of upper hemisphere to figure out the metric component. What you need to do, calculate the metric component using the parameterization of lower hemisphere, and you will see, so let me write this as Gij plus. So these are the metric components for the upper hemisphere, and you will see that this will turn out to be the same for the lower hemisphere also. Okay, so I don't have to do anything, simple thing, these will be the same. So most of the work has been done. We have the metric component. Now, if I will write the complete metric using this expression, it might be uh, quite complicated looking. Okay, it may look quite complicated. So let me just take a particular case. What's the particular case? Particular case is n equals to 2. That is, I'm talking about two sphere sitting in R3. Okay, that's what I'm talking about. So this my so let me write down all the metric components in the matrix form. Okay, so what I am going to write down this matrix Gij. So let's call it the matrix A. Okay, so what will be the G11? G11 will be 1 plus x1 square divided by 1 minus x1 square minus x2 square, because we have the two sphere sitting in R3. That's why. Okay. What will be G11? So I'm writing down in the matrix form. So here you will have the 1 2 entry. So in case of 1 2 entry, delta Ij will be 0. So this will be x1 x2 divided by 1 minus x1 square minus x2 square. Now G21 will be equals to G12. So x1 x2 divided by 1 minus x1 square minus x2 square. Now G22, in case of G22, delta Ij will be 1 and x2 square divided by 1 minus x1 square minus x2 square. This is your matrix of the metric components. Okay, so this is your Gij metric. Now, when I explain the Riemannian metric, the expression for the Riemannian metric in terms of line element, you remember ds square Gij dxi dxj. I also told you how to write it using the matrix. So what you will do to get ds squared, you will simply, so this is two sphere, so I'm sorry, dx1 dx2, your matrix, the column vector dx2, right? So now this is just calculation. I hope you can do the calculation because this is simply matrix multiplication. You can do the matrix multiplication. So ultimately, after calculating what you will get here, you will get ds squared equals to dx1 squared plus dx2 squared plus x1 dx1 x2 dx2 whole squared divided by 1 minus x1 square minus x2 square. So please verify it. Verify it. Okay. You just need to do the matrix multiplication here. Okay. This is just matrix multiplication. There is nothing complicated here. We have been doing it since 12th class. Okay. Matrix multiplication, some simplification, and you will get this matrix. Okay. So just by looking at it, this is for two sphere. You can write it for n sphere. Just by looking at it, you can see that for n sphere, how this will look like. This will look like ds square. You have this, the summation dxi square, and I will run from 1 to n, plus here you will have what? You will have summation xi dxi, and I will run from 1 to n, square, right? That's what the numerator is. And in the denominator, you have 1 minus summation you have summation. So what is this? This is again xi squared, and I is equals to 1 to n, right? That's exactly the metric for the entire n sphere, the unit sphere. Okay, I hope you all understood what I did. There was nothing complicated here. We simply wrote the simplest parameterization for the sphere, which can be written down using this simple condition of the norm that you have. The norm of x is 1. Using that, I formed this n plus 1th coordinate. That was the only coordinate that was missing for me. Okay. And then we found out these del phi over del xi. Using that, we figured out the metric component G11, G12, G21, all these Gij's, and then we wrote the expression for it. In case of two sphere, we wrote the matrix, and using the matrix, we can write this entire expression for Riemannian metric in terms of line element. Okay, so this is in case of your Cartesian coordinates. So this is in case of Cartesian coordinates. Okay. Now I want you to do one thing. This is an exercise for you, that calculate the Riemannian metric not for Sn, just do it for S2 contained in R3 with spherical coordinates. Okay. So what are the spherical coordinates? The spherical coordinates, you already know the parameterization. Let me give you the parameterization. So this will be x equals to uh, r cos theta sine phi. So this is for S2 of radius r. Okay, I'm taking S2 with radius r because it's simpler case. It's simply S2. So I can also take a general sphere r. Okay, general sphere of radius r. No need to take the unit sphere. You can literally take the unit sphere. There I took the unit sphere because it was the n sphere to make the calculation a little bit simpler. That's all. Okay. So y equals to r sine theta sine phi, and z equals to your r cos phi. Okay. Now here your theta is the polar angle. So this theta runs between 0 and 2 pi. And this phi runs from 0 to pi. Okay, so this is your polar angle. And what is this angle? So this is angle measured down from z-axis. I hope I don't need to explain this because this is your undergraduate calculus. In your undergraduate calculus, you have derived these spherical coordinates using the polar coordinates and everything. You have derived all these things. So figure out the Riemannian metric using this. If you are wondering how, I would advise you to go back to my lecture on the example of Riemannian manifold where I took the Euclidean space. In case of Euclidean space, I took the polar coordinates and I did all the calculation in polar coordinates to determine the Riemannian metric on Euclidean space. The same calculation will be done using the spherical coordinates here to do this. Okay, that's all for today. Thank you very much for watching. See you next time.